So I have this skateboard at an angle with mess 1. I put oil here so there's no friction there. Then I have the second surface with mess 2, which I'll be adding water to.
Now we've got the coefficient of the two surfaces. In here, I will call it mu1 and mu2. The weight of the glove box is 0.1 kg, and 0.7 kg is the minimum weight of the bottle for the glove box to move outwards. This is the diagram I drew to show the experiment. The two angles are 46 degrees and 39 degrees. The direction of the bottle's motion is downwards, which means the friction force F2 acts on the opposite direction and is upwards. When the box starts moving upwards, F1 acts downwards. The normal force N1 and N2 acts perpendicularly to the two surfaces. Let's look at the right-hand side. We use the same method to get T2 equals to 1.4648 Newton. Now we can notice that the tension forces T1 and T2 are different, but they were supposed to be the same, because at the point the rope touches the bike, only changes the direction of the force. The difference may due to the friction at that top point, our limited equipment, and the surroundings. To make our data more accurate in this experiment, we did 3 trials while finding the coefficients and got the average angles. We added oil to the point where the rope touches the bike, so friction force is minimized at that point, and the experiment was also done 3 times.
For the second part of the assignment, our group decided that we wanted to conduct an experiment around the topic of moment and equilibrium. With this in mind, I went around my house to see what I could find. After wandering around for some time, I found 2 planks of wood, 2 5 kg weights, a 2.5 kg weight, a scale, some measuring tape, and 2 heavy boxes. Once all the equipment was found, an idea to create a system using one of the wooden planks as a pivot and the others as a surface for the forces to act upon came to mind. However, before I could start balancing out weights and their moments, I needed to first take a few measurements. Using a scale, it was seen that the wooden plank weighed 3 kgs, and all the weights matched their label. After that, I measured the longest side of the plank to find out it was 97.5 centimeters long. After finding these measurements, a method needed to be planned, and after some thinking, we decided to conduct 3 trials. For the first trial, we wanted to move only the pivot, so here, we placed a 5 kg at the end of one board, and moved it around until the board was balanced. After taking some measurements, we found that it was roughly 18 to 20 centimeters from the end. Similar to the first test, the second test is put into equilibrium by moving the pivot below. Here, we can see we got 2 5 kg masses, as well as a 2.5 kg mass. These two, positioned at different lengths, create an equilibrium. The moment of this is equal to the moment of that. That's found by taking the total mass times gravity, as well as the distance of 26 centimeters, and the same done for this. Unlike the first two trials, this trial is done by positioning the pivot right in the middle to see the effect the weights have. Here, we can see a 2.5 kg mass holding up a 5 kg mass, but their length is different. As you can see, the 2 kg mass is placed roughly 40 centimeters, while the 1 kg mass is placed roughly 20 centimeters. You could say that that the length or the mass is the length is disproportional to the mass. So as one increases, the other one must decrease.
Our second experiment covers the idea of static equilibrium. For a body to be in static equilibrium, the sum of the forces in the vertical direction must equal 0, the sum of the forces in the horizontal direction must equal 0, and the sum of the moments at any point on the body must be equal to 0. Conventionally, forces acting upwards are taken as positive and forces acting downwards are taken as negative. Forces moving to the right are written positively and forces moving to the left are written negatively. Moments acting in the anti-clockwise direction are taken as positive and moments acting in the clockwise direction are taken as negative. It is important to note that there may be a slight variance between the theoretical outcomes and the practical outcomes. This is because of any minor errors that could occur, such as rounding or the fact that in real life the weight does not actually act at a single point. In this experiment, the total length of the block is 97.5 centimeters and it has a self-weight of 3 kgs. In this working, newtons will be used as the units for force and meters for the units for distance. In trial 1, the pivot is placed 20 centimeters from point A. A 5 kg, 49.05 newton weight is placed an unknown distance. The vertical forces in this body need to be added together to equal 0. In this equation, there is one unknown, the vertical support force of the pivot point. Rearranging this equation, it can be found that the vertical support force of the pivot point is 74.48 newtons. Taking the moments from point A, there is also one unknown. Rearranging the equation, it can be found that the weight must be placed 0.028 meters from point A in order to achieve static equilibrium. In trial 2, a 10 kg weight is placed at one end, with the pivot point 25 centimeters from that. A 2.5 kg, 24.53 newton weight is placed at an unknown distance. Adding the vertical forces to 0 finds the vertical support force to be 158.06 newtons. Taking the moments from point A finds that the 2.5 kg weight must be placed 96.5 centimeters from point A. In trial 3, the pivot is halfway. A 2.5 kg weight, 24.53 newtons, is on one end, and a 5 kg, 49.05 newton weight is placed at an unknown distance. Adding vertical forces together, the vertical support of the pivot point is found to be 103.01 newtons. Working out the moments from point A, it is found that the 5 kg weight must be placed 24.4 centimeters from the end in order to achieve static equilibrium. Moments are calculated by multiplying the force and the perpendicular distance. This means that the force and the distance are inversely proportional. This can be seen here as a 2.5 kg weight is placed on one end of the block, the pivot in the middle, and the 5 kg weight, which is double the other weight, is found to be placed halfway between the pivot point and the other end. This means that the force and the distance are inversely proportional.